Heavenly Father, we thank you for your loving kindness to us. Thank you for this day. And we pray, Father, that you would take this time in our lives and do something with it. Some are here visiting and some are not. Lord, doesn't make any difference to you. You can take this day and make it meaningful, not only for our lives, but for someone else. And I pray you do that, Father, and I'm asking you to do it in Jesus' name. Amen. Amen. Okay. So, sorry about that. Some people would be distracted if I left that on. That's the three sounds out of they were a jazz group combo out of the 50s and 60s and 70s. They're really good. I like them anyway. So, we're going to study weather and climate. That's what's happening today. You can see it outside here in eastern Kentucky. You don't know what the weather is until you're in it, because it changes so much, at least because of the mountains, the narrow valleys. There's a whole lot of contributing factors to what we have right here in Breathitt County. In fact, I've got a thing on the flood in 1939 where it dropped 11 inches in 4 hours in the hills. And so both sides of the hills were flooded, and 20-foot wall of water, you probably heard this, 20-foot wall of water came down the mountainside and washed everything away, washed buildings off their foundations. So, but the weather system was really interesting. What was happening to make it drop 11 inches in 4 hours, probably about like that, in 4 hours. Plus, it wasn't just a flood of water that came down, it was a flood of everything. Water didn't, I mean, if it was just water, people would have survived, but it was trees and fences and cars and farm implements. I mean, everything was down.
I think 2.75 inches an hour.
It was heavy. So, but that was Breathitt County back in the day. So right now, the study of meteorology. That's what we're studying right here. Now, this is a class on meteorology. If you went to a university and you studied meteorology, you would have several years of this stuff. So this is like my mother said, it's a sweep and a promise. It's, well, I'm sweeping this up quick. I promise to get back to it later. Okay, this is it's very much of a survey. So, but there's a difference between weather and climate. Weather is a word to denote or illustrate the state of the atmosphere at a particular place for a short period of time. So right now the weather is, it's raining, it's overcast, right here. That's what the weather is. And the weather constantly changes. In a little while, it'll be different. Yesterday it was raining in the morning, and the day later it was beautiful. So weather is constantly changing. Climate is not that. Climate is not the same as weather. Climate is an aggregate composite of weather. So you're looking at the whole area. What is it generally? Like in November, like in December, or no, in January, when my sweet wife and I came here in 1994. So we arrived here in 94. In January, there were 17 inches of snow on the ground. That's very unusual. It averaged 20 degrees for the whole, that was the average. Now, from Alaska, that's a piece of cake. But here in eastern Kentucky, 17 inches of rain and an average of 20 degrees across the whole of January, that's significant. So, but you wouldn't, if you were talking about the climate, you wouldn't, oh, this is what happens. No, that was weather. Climate is what generally happens in January in eastern Kentucky. And so you'd look at what happened for the last 25, 50 years in January, this is what we have, and you'd do averages. And so you get a general sense of what was going to go on. Generally, it's colder in January, and it's this much colder than it is, but it's an aggregate. It's a composition of a bunch of stuff. So I couldn't find it. Well, I will for Glad, won't help you from Mount Carmel, but I had it, I had a guy from the weather station that described what it was to evaluate the weather, how you're gonna predict the weather and how complex it is. So these things, air temperature, humidity, type and amount of cloudiness, type and amount of precipitation, air pressure, and the speed and direction of the wind. All those go in to what the weather is. And if you're doing, and this is a gas, I mean, what we're breathing is a gas. And so there's gas all over. And you probably know, you've got cold fronts coming in and warm fronts. You have all these dynamics to predict the weather. They use models. They have another average. And when they look at what weather is supposed to be coming this way, they try to pick a model that will predict perhaps what they could do. In fact, one of the weathermen that had his first job in somewhere in Kansas. And so to get the weather, an accurate picture, they have a balloon, a weather balloon, and they have an instrument that's about like this big, plastic encased, that they send up in the weather balloon. And as the weather balloon rises, it expands. In fact, I don't know if you've ever seen pictures, but some of them expand to as big as like a Volkswagen bus. I mean, as they rise, there's less air pressure, and so these balloons expand. And they get to a certain point, and they break. That's what they're designed to do. And then this little box has taken readings as it ascends, and then the thing bursts, and a parachute is supposed to come out, and then this thing slowly goes back and records as it comes back. And it hits the ground, there's a little name. If you see this, call the weather station, and you call them, and they say, where are you? And so they come out and get it, and then they get the data from it. Well, this guy, he was a relatively new weatherman, and his job was to pack the parachute on the back of this thing. So he did that, except he put the parachute on upside down.
Uh-oh.
So this little box, encased in plastic, that had all the weather instruments, fell straight down. It didn't slow down, it fell from whatever height it got to, it went straight down. And unfortunately, he hit a cow, and it killed the cow. It would kill anything that it fell from that distance. Well, he never got to pack a parachute again. He was still a weatherman. In fact, he worked out here for a while. And he was he was a funny guy. But he didn't do whatever he did to be funny. So anyway, these elements, air pressure, air temperature, humidity, type, and amount about cloudiness, type of precip, air pressure, and the speed direction of the wind constitute the variables.
Do you think you could go to like the very top?
No, I'll get it later. Okay. Can't do that. So these elements constitute the variables from which weather patterns and climate types are deciphered. A change in any one of these elements will bring about changes in the other. So one thing changes, it affects the others. So they're all interrelated. So you could have 4 of the 5 just plugged in exactly, and you have one that doesn't plug in, and it can change the whole dynamic of the weather. I'm not a weatherman, but it's interesting how when they try to predict the weather, what a difficult task it is. I have more sympathy for those that are predicting it because of what they have to try to predict with. I mean, they have instruments, they have all these things, but you're trying to estimate, well, if that wind is blowing here, I'm going to estimate it's going to get here at this point. Well, it's all estimating. You're all conjecturing that it will. And sometimes they tag it and sometimes they don't. So these elements are interrelated. So for those in this class, you should probably know that these 6 elements, there are 6 of them, are interrelated. If one is changed, it'll affect the others. Composition of the atmosphere. Air is not constant. It's not the same everywhere. Water vapor, dust, other variable components were removed from the atmosphere. If they were, we would find this composition is uniform. Nitrogen, 78%, oxygen, 21%. That's basically where it is. Though these gases are the most plentiful components in our air, and significant attribute or part of our living, they are of minor importance affecting weather phenomena. Now, I'm going to take a departure because I can do that. Yes,
May we introduce ourselves to the college students?
not yet. I want to take this departure.
Okay.
So, this is Mount Everest.
Wow.
So I don't know if you thought, but this is how I get sidetracked. So I was doing this and I talk about hypothesis building, and we'll get back to that probably the next time I do it. But I thought about hypothesis building. I thought of going up this mountain because they went up in an air balloon, these guys. 3 guys went up in an air balloon. They hadn't been up as high as they went up, and only one of them lived to tell a story because they made assumptions about things and the assumptions weren't right. They were good scientific assumptions, except they were in air, and 2 of them passed away on the way. So I thought of Mount Everest. So Jackson, Kentucky, in town, is about 774 feet high. And at sea level, if you're right at sea level, and here's the ocean, and then land right here, the air pressure is about 14.7 pounds per square inch.
What about 101?
What's it?
It's also 101,325 pascals.
Okay, good. Well, we're not gonna get into pascals.
I'm
We're just
sorry.
gonna, no, you're okay. We're gonna talk 14.7 pounds per square inch. So that's at sea level. So 774 feet is 14.29. I mean, that's hardly a difference. And the highest place in Breathitt County is about 1,600 feet. So that's about a third of a mile, less than a third of a mile up. And it goes down to 13.87. But when you're talking about Mount Everest, the base camp, the camp that you come to start on, you arrive in Kathmandu, you hike, I don't know how many miles it is, to base camp. Base camp is 17,651 feet. That means it's 3.5 miles high. So it's another 3 miles up from the highest point in Breathitt County. 3 miles straight up. Well, the air pressure, the pressure that you would be attempting to breathe, is about half of what you would get at sea level. Not exactly, but about. So, you start at this base camp, and what they do, the climbers, they go from base camp, they go to the first level camp, and then they come back and recoup. They have to get their bodies adjusted to this altitude. So they go to the base camp, go to the first, then back to the base. Then they go to the first and second and back to the base. And then they go to the first and second and third and back to the base. And they stay a little bit of time in each higher camp and then come down to the base camp to kind of recoup. And then they do it again, just to get their bodies acclimated. And I don't need to go through all of these, but the camp 1 is a little bit more than almost 3 3/4 miles. Camp 2 is about 4 miles up. Camp 3 is 4.5 miles approximately. Camp 4 is 5 miles, almost 5 miles, 4.92 miles. And the air pressure is only 5.22 pounds per square inch. And the summit, the top of Mount Everest, is 29,032 feet, or 5.5 miles up. The air pressure is 4.56. That's a little bit more than a third of what it is on sea level. 20,000 feet. 20,000 feet is about the maximum that you and I could take in enough air to continue life with. Now, the people that can do it are people that have trained themselves. I can't run a 4-minute mile. I've never been able to run a 4-minute mile. Few people can, more now than ever. I was alive when the first person ran a 4-minute mile. I think it was 1954. Well, now, with development, I mean, people exercise, they do weights, they do training. In fact, a lot of people, a lot of runners train in Denver, Colorado, because it's a mile high. So the air is thinner. It's 12.1, I think, pounds per square inch. So it's less. So it takes more effort to take in air. You just have to work harder to get in the same amount of air. And if you're running, if you've exercised yourself in taking in air by running at high elevations, then when you run in low elevations and there's more air to take in, you can do better. Because you've developed your lungs to take in that air. It's not just you're a good runner and so you could, if two people were equal and one of them trained at Denver and one of them trained at sea level, you'd find that the guy that trained would probably do better just because, or the girl, because they could take in more oxygen. They were trained to take in more oxygen and process it better than the one that was trained at sea level. So the air pressure makes a difference. And most commercial planes travel at 30 to 40,000 feet. So that's six and a quarter miles up. And that's only 6 1/4, that's only 3/4 of a mile above the summit of Mount Everest. And there are people that do Mount Everest without extra oxygen. But if you ever read how arduous that is, because people die all the time trying to ascend Mount Everest because of the lack of oxygen. Because lack of oxygen, like the weather, or like the weather has so many variables. Well, there are several things you can get because of lack of oxygen. And some of it, you get disoriented. And people that are climbing Mount Everest, sometimes they get to the point where they start taking off their protection. They take off gloves, they take off their coats, they become disoriented, probably to say it lightly. And they can get, the things happen in their body, with their blood. A lot of different things can happen. So at an elevation about 2,000 feet above sea level is the maximum height at which sufficient oxygen exists in the air to sustain us. You can develop an ability to surmount that, but you'd have to do that. And some of you perhaps would be able to do that in easier than others. I mean, we're all designed differently. God designed us all not the same. Okay. There never has been any two human beings that have been the same since Adam and Eve, and they weren't the same. So, that was a deep departure. So, these gases are the most plentiful, nitrogen and oxygen. Those two gases are the most plentiful. Those two gases are the most plentiful. Usually when I repeat it, it means if you're in this class, you should probably put a star by that thing, because when you comes to test time, which is inevitable, it's inevitable, you'll be doing that. You will probably see something like that on a test. So the components there are of great significance to life on Earth, but they're minor importance in the affecting of weather. So they're the bulk of what's happening. I mean, 78% and 21% is 99%. So there's only 1% left. But the 99% are not the most important. They're of minor importance when it comes to the weather phenomena. They're important for you and I to be breathing, but for weather, to this stuff that goes on, when we look out and see weather around us, that they're of minor importance. Meteorologists had to choose the most significant component of the atmosphere, they would choose water vapor, water vapor, water vapor.
Yay, H2O.
Why such a small fraction of the atmosphere is so significant? It's the fact that water vapor is the source of all clouds and precipitation, but also has the ability to absorb heat energy given off by the earth as well as some solar energy. When water changes from one state to another, it absorbs or releases heat energy, latent heat. Latent heat, we're going to talk about that later, but it plays an important role in transport of heat from one region to another. Its energy source, it's the energy source that helps drive many storms, which we'll discuss later. This latent heat, especially when hurricanes develop, and they develop over water, and they develop over warm water, because you have evaporation, and that just feeds this mechanism. As the storms come across the Gulf of Mexico per se, and get in line to hit Louisiana or Florida, they come across the Gulf of Mexico, they're picking up moisture from the evaporation of the water that's warm, and then that translates into latent heat, and so you've got things happening weather-wise that are significant. Okay, the extended structure of the atmosphere. This is divided into 4 layers on the basis of temperature. So they're not clear. It's not like, okay, you get up to this high, and this is the line that this changes, and then you go up here, and then you have another line. It's all approximate, because our weather, it's a gas. If it was a solid, like if it went up 7 feet and it was concrete, you'd know when you went from the concrete to something else. But in this case, it's all a gas, so it's all moving together. So generally speaking, this is averages. In fact, the troposphere, which is the bottom layer, that's what the level we usually are suspended in. The troposphere, it's about 11 miles thick at the equator, but on an average, about 4.7 miles thick overall. So it's thicker at the equator, and the average, which means it's not only thicker at the equator, but it's a lot thinner in other places. This is a troposphere. That first level of the atmosphere is only about 7.4 miles average overall. So people would say, well, the troposphere is 7.4 miles thick. And that's an average. It's thicker at the equator. It's not as thick in other places, but it's an average. So, and averages can be deceptive. If I took Gail Finney, for you, I'm not going to know Beth Finney's wife or husband. So if I took him and took Dr. E, there would be quite a difference. If I took their average height and say, of the professors here at KMBC, the average height is such and such. Well, that may not be accurate, because one is significantly taller and one is significantly shorter. So it's an average. It is, and that's why in statistics, just for your information, in statistics, you need a wide body to represent people. If you just take a couple, in fact, some statistics that they say, this is statistically significant. You have to look at how many people are surveyed. If just a handful of people are surveyed, that's not enough. They'd say, well, they just throw it out. That's not significant. So anyway, practically all clouds, we're talking about in the troposphere, this lower layer, practically all clouds and precipitation, as well as violent storms, form in and are restricted to this layer of the atmosphere. So the lower layer of the atmosphere is where all this stuff is generated. Tornadoes, all this stuff is generated. Hurricanes, clouds, rain, it all is generated there. For the most part, I mean practically all. The average temperature decreases in the troposphere, and that decrease has actually been measured at 3.5 degrees Fahrenheit per 1,000 feet. So if you go up 1,000 feet, it'll be 3.5 degrees, 3.5 degrees less in Fahrenheit. And if you go another 1,000 feet, it'll be another 3.5 degrees reduction in temperature. And that stuff is a normal lapse rate. We will dig into that later.
Oh, that's the one I forgot.
So, and then the stratosphere. That's where planes fly usually. They fly in the stratosphere because there's less air up there. The air pressure is, if it was, so the air pressure, I think I said it was 6.2, at 33,000 feet, it's about 6.25, and at 40,000 feet, it's even less air pressure. Well, not 6, less than that. So it's really thin up there. So because it's really thin, there's less drag on the plane, so it can fly faster. Now, there's also the wind currents that surround the Earth, the jet stream. And the jet stream they didn't figure out there was a jet stream until World War II, which is in the 40s. And they had a bomber going on a run,
A flying.
B-20. I'm not sure it was a B-25 or it was a larger plane than that. Anyway, it's going on a bombing run, and it flew up really high to get out of the radar of the German radar. German or Japanese, I'm not sure, but whoever it was getting out of the radar, so it flew really high. Well, it got in the jet stream, and all of a sudden, this plane, it was designed to go so fast, maximum. Well, it was redlining its speed. I mean, it was zooming, and they didn't know why it was. But all of a sudden, this plane just took off. So they were having trouble dropping their bombs because it was screaming. And so when they went to evaluate why it was doing that, they found there was a jet stream. Now, the Bible talks about air currents in the air that would suggest a jet stream, but they weren't reading and interpreting that. So anyway, so that's stratosphere. It remains constant. Temperature declines from our Earth. If you go in the troposphere, the temperature declines at 3.5 degrees Fahrenheit every 1,000 feet. And then you come to the stratosphere. And so it doesn't just decline anymore, it levels off and goes at a constant rate, and then it begins to increase. So gradual increase, which continues until a height of about 29 to 31 miles above the surface. And the ozonosphere, or the ozone layer, lies between 6 and 31 mile range. So right in the lower troposphere and into the stratosphere, that's where the ozone layer is. So it's not uniform. The increase in temperature is because this stuff here in the ozone layer, it absorbs heat. Incoming radiation, radiant energy comes in that would be damaging to you and I, and it's absorbed by the molecules in the ozone layer, and so that's why that area heats up, because the absorption generates heat. So, the oxygen molecules in this layer are split into single atoms of oxygen after absorbing ultraviolet radiation emitted by the sun. So ultraviolet radiation would do us damage. As this class knows, that you have the visible light range from red to violet, and going toward violet, you've got ultraviolet and X-rays and gamma rays. Well, the ultraviolet and X-rays and gamma rays are bad because they are high frequency and they penetrate our bodies, and they can do damage when they do. So we want to avoid ultraviolet, and the way God designed this thing is that there's a protection layer. And that's the ozone layer, and some of this ultraviolet radiation, radiant energy that's coming in from the sun, or cosmic radiation that's coming in from outside our solar system that gets into the mechanisms that are there, this ozone layer does a good job of absorbing this stuff. So it generates heat, so you get an increase in heat. But there's so much less air up there. You can heat it up and you might not feel any difference because the molecules are so spread apart, and it gets that way as it goes higher. So anyway, the presence of the ozone layer in our atmosphere is of vital importance to those of us on Earth because of the capacity of this ozone to absorb the burning ultraviolet radiation from the sun. So, and there are different kinds of ultraviolet radiation. Ultraviolet A, B, and C. It absorbs all of C, 95% of B. Ultraviolet A, it only absorbs 5%, but that's not so bad for us. And we'll talk about that. We'll talk about that later. We're going to talk about tanning salons. I really like Showtime, but going in and getting a tan is not anything that I would recommend anybody do. It might be fine now, but it's not without possible consequences.
Oh, come on, Mr. Nelson, you could order a pizza while it's baking, you can go bake in the table.
I know, but the pizza will be gone in a little while, and I might be gone sooner than I think. So I don't want to be gone sooner than I think. I want to be gone soon enough, but. So, in the mesosphere, which is the third layer, temperature again decreased with height until approximately, and they've only increased in height because of the ozone layer. That's absorbed, and absorbing has generated heat. But then you go up high, you don't have the ozone layer, you have, and then temperatures decrease in height until about 52 miles above the surface, where the temperature report minus 90 degrees. And then extending upwards from the mesosphere, but having no well-defined upper limit is thermosphere. That's the last layer. In the extremely rarefied air of this outermost layer, temperatures again increase due to the absorption of very short-wave solar energy by atoms of oxygen and nitrogen. So they're atoms of oxygen and nitrogen, and they do some absorption again of some of the shorter wavelength rays, and so that increases. So you have a decrease, then it levels off and increases, and then it decreases, and it begins to increase again. So it's those points that they are evaluated, so that temperature is defined in terms of the average speed which molecules move. Temperature. So like I talked about the sun, so so the sun's surface, as you remember, is 6,000 degrees, about. So the chromosphere, which is the layer above the sun, is up to a couple million degrees. So you think, boom, and you just burn up. Well, if you got into the chromosphere, if there wasn't the sun's surface to deal with, there are so few molecules in that you could probably last. It's a million degrees, but there's so few of them, it wouldn't like you'd be stepping into like a boiling pot of a million degrees. It would just be a bing, bing, bing. It wouldn't be that intense. But because of the heat that's generated from a 6,000 degree surface, you'd become crispy right now. So, if the atmosphere had relatively, well, here's a picture. So if the atmosphere was moving very fast, we would conclude temperature was high even if it wouldn't feel hot to the touch. And that's what it wouldn't feel hot to the touch. But molecules would be moving very fast. That's how they determine heat. And so that would be, I don't determine heat that way. I just go, and it's hot, I got it. I don't have to touch it, I can get close to it. Well, I don't know if any of you have been around electric stove. Electric stove, my grandma, she had a wood stove. So she could tell from the heat where the heat was right for a baking pie or baking bread. She'd been doing it for so many years, she could tell by feel of the heat when it was the right temperature to do it, and she just put wood in that thing. Well, electric stove, you don't necessarily get that. It's on, and you turn it off, and the burner isn't hot anymore. The burner looks cold. But if you put your hand on that burner, you're gonna get the marks of that ring, because it isn't cold. And that side is not in ultraviolet, that's infrared. So the thing, you've got a visible thing, it's visible when you see the red of this burner. So that's visible red. But when you turn it off, you lose that. It's not radiating at that wavelength anymore. It's infrared. You don't see it, but it still will burn you. Now, it won't burn you forever, because it'll continue to cool, and it's cooling, and so the wavelengths are getting longer and longer, and so and eventually they get to the point where you can put your hand on it and it won't burn.
And then the other two ones are microwave and radio.
That's right, and radio up to 6 miles long.
Whoa.
So here we have a chart. Now, for you in this class, I will post this if I remember to. In lesson, I don't remember to do that very often, but I will, so you will have this thing if you want to look at it. But there you have the troposphere, it's heating up, the stratosphere, same, and then cools, mesosphere heats up again, then it declines this cools down again, and then it heats up and so that's atmospheric pressure. So atmospheric pressure is the weight of the air above us. So if we were to take a box, 1 foot square, I think it's 1 foot, or is it 1 inch?
Yeah, it's.
And shoot that up 60 miles. The weight that is above us would be 17.4 pounds per square inch. So it is inch. So square inch, a column of air, at sea level, 60 miles above us would weigh that much. The weight of the air. Molecules have weight because of gravity. Gravity, trying to pull things down, well, it doesn't try, it doesn't. So, on Earth there's a relationship, approved by the Dean of Students, between atmospheric pressure and altitude.
Why is it
Well, he just needs to approve
That's
everything.
solid.
That's good. So, as you increase in height, the atmospheric pressure decreases, as we saw with Mount Everest. The higher you go, the lower the air pressure is. There's less air above you, and so there's less weight of air above you. With less pressure, the number of molecules, primarily oxygen and nitrogen, here on Earth are freer to expand. Without pressure, they can expand. That's why that balloon that guy sent up for a weather balloon, they sent it up. They can fill it up so it takes off, but the higher it rises, there's less pressure holding it in, and so it expands. And they have that thing designed so it'll get to approximately a certain height before it explodes. Now, some of them have not been made exactly right, and so sometimes they've gone as high as being in the traffic where planes have seen them, which is a mistake in how they're designed, they're built. They did something wrong in the putting them together. Anyway, free to expand, so fewer of them occupy the same area. The result is that the air becomes thinner. For example, at sea level, 14 pounds per square inch. You move to Denver, which is about a mile high, you would feel lighter, have to breathe heavier because of every breath you take. There are fewer oxygen molecules inhabiting it. So fewer oxygen molecules to take in that we need to have taken in, we have to work harder to do it, and that only goes down to 12.1 pounds per square inch. So, molecules have weight. Now look at that, I said remember. That might be significant if I'm saying remember. The absence of atmospheric pressure is a vacuum. So interstellar space would be what we'd consider to be, there wouldn't be atmospheric pressure there. So about 10 miles up, about 10 miles, 90% of the atmosphere has been traversed, would be below you. So you covered, at 10 miles, you covered 90% of the atmosphere. And above 62 miles, only 300,000ths of a percent, not of 1%, little tiny, of all the gases composing the atmosphere remains. So if it's up above 62 miles, there's hardly any up there. There is some, but it's very small. At this latitude, density of the air is less than what can be found in the best artificial vacuum. So it's really, with an artificial vacuum, they can only extract so much from it, apparently. To say where the atmosphere ends and outer space begins is quite arbitrary. There's no definitive sharp boundary. Vast bulk of the gases composing the atmosphere are very near to the Earth's surface. Okay?
There's about the boundary to space. Some people have said that there's the Kármán line at 62 miles up where the space begins, called the Kármán line.
Well,
But
they're saying it's a line because they're saying that 62 miles, but it's all gas, so it's kind of fuzzy. It's like the Earth's, the sun's surface. It's a gaseous body, so this thing is variable. It's not just like a line, it's not just like the desk. I mean, you can come this far and you're gonna hit this desk. There's a line to it, you're gonna feel it, no question. So if we were living in Denver with thin air, and then we came back to fly to Van Cleve, and your flight attained an average jet flight altitude, so he's looking at this thing, and at 35,000 feet, the air pressure would decrease to about 3.4 pounds per square inch. Your ears would pop a couple of times, and the cabin pressure was equalized to adjust to your body comfort zone. So when you're sitting in a plane, things seem pretty normal. I mean, you breathe easy, you don't have a problem. But that's because you're sitting down. But usually, air pressure in a plane isn't set to sea level temperature. It's set to about 8,000 feet. So at 1,000 feet, if you were have to work at this level, you would notice the difference between working, if you were working here and you were working at 8,000 feet, you would notice a difference. It wouldn't knock you out, but you would notice you would have to work harder and breathe harder to get in the same amount of oxygen. So, but that's what they set it for, because everybody's sitting, and so thinner air isn't a problem. You're sitting, you're relaxed, some of you are relaxed, some of you might not be. I mean, flying in a plane, I love it. I love to be able to look down and see, you know, when you cross the country, you see patterns, you see mountains. If you're at night, sometimes if you're flying high enough, you can look down and see weather action happening down below you, lightning and thunder and stuff. You see sunsets and sunrises that are just incredible. And once you're in the plane, you can't do anything. You can worry, but it's unprofitable. What are you going to worry about? There's nothing you can do. You're at the mercy of the plane and the pilots. And so you might as well just give it up and say, well, God, I'm here. So it's important to be ready. I mean, if you're saying that and you're not ready to meet God, then that's another, I guess that could cause some worry. But flying is just so much fun. I mean, you're seeing things that you never see otherwise. And the clouds are all white up there. There are no black clouds up there, they're all white. Why is that? Because the sunlight, the visible light that we see is white until it's refracted. But it's hitting the clouds, and the clouds remain white. When we look out here, well, it's overcast altogether, but it's kind of gray. But if we see clouds out there that have black bottoms, that means that the sunlight coming through it is being, what we're seeing, the shadow of moisture, frozen or regular water droplets that are reflecting the sun back, and so it's not penetrating through, so underneath the clouds are gray. The grayer they are, the more likely you're gonna see rain or snow, and that's true, because there's a lot more reflection and there's a greater shadow. There's more rain droplets, there's more frozen droplets. So anyway. So, why do planes have little yellow oxygen masks that they show you how to use while you are fooling around with the magazines in the seat pouch in front of you? In case there's a sudden loss of air pressure in the aircraft, and it would naturally adjust to the very low pressure outside of it. So if it was 3-point-something pounds per square inch flying at 40,000 feet, and all of a sudden there was a hole in that plane, and so there would be a great equalization. What was inside the plane would try to equalize with what's outside. So you'd have a rush of air out of that plane, and your pressure in there would drop, and you'd drop too. So these little things, so you can put them on your thing and put them on around your face before you put it on your children, so you can still do it and not be trying to put it on there and you're gone. And so anyway, they suggest that. So air pressure goes from high to low. So it would be higher inside the plane than it would be outside. And so try and equalize. So the air pressure inside would be drawn out immediately. So in December 2005, an Alaska Airlines flight 536 left Seattle for Burbank, California at 3:45 p.m. The plane took off, began to climb in altitude. About 20 minutes after takeoff, they noted a loss in cabin pressure. Passengers noted their ears were popping, and one of the passengers, a general aviation pilot, recognized it was a bad sign. Shortly after the little yellow oxygen mask dropped down, they were flying at about 26,000 feet when this happened. The outside pressure at 26,000 feet was about 5.4 pounds per square inch. So 14.7 at sea level, 5.4, that's almost a third, would make it difficult for breathing. So the plane returned to Seattle and found a hole measuring 12 by 6 inches just behind the top of the forward cargo door. So, oh yeah, we don't have time. When are we out of here? 05? Okay, don't have
It's almost 11.
I know. So anyway, 1947, I was a little more than 5 months old when this took place. I didn't know it happened. I wasn't paying attention. I've done that all my life. But this one, Captain Chuck Yeager took Bell X-1, an experimental rocket-powered aircraft, to the supersonic speed of Mach 1, 768 miles per hour. Now that's a little variable. The Mach, it depends on, there are a number of things that would factor into that. But anyway, he traveled that fast for the first time. He was the first man to travel that fast. He was in a jet. Mach 1 speed represents the speed that sound travels, different rates, whatever. So, in August 16th, 1960, 32-year-old U.S. Air Force Captain Joe Kittinger ascended in a helium balloon tethered gondola. So he was in a contraption, a gondola, that took him up with an air balloon to about 19 miles above the Earth. and he jumped out. So he jumped out of that plane. And his free fall, falling from that height, lasted 4 minutes and 36 seconds. And he hadn't hit the ground yet, he was just free falling, no parachute, just going, whoo! So he was traveling, his body, now he had a suit on, he had all this stuff on. This is 1960. But he traveled about 600 miles an hour, falling down, before he opened his parachute around 14,000 feet. So the Stratus project, I don't have time to show you this, but if you get online, I'll show my class this next time. It's really cool. So Red Bull sponsored a guy to go up higher than him and jump. And they have it filmed. It's really, it's well done. I mean, they spent thousands of dollars, millions of dollars to do this thing.
How far up was he?
Who was that?
The Red Bull guy. Because I've seen him before, I just can't remember how far.
Oh, he was
actually
up.
high.
He was up 20 some mile, let me see. He reached the maximum spot, okay. He traveled faster than the speed of sound, 843.6 miles per hour. And he went into a flat spin, and if he hadn't gone out, if that's a concern they have, if you're falling, free falling, and your body, you begin to rotate like this, so the blood in your body would go to your head and your feet. Well, if you got a lot of blood going to your head, it can cause, you can get embolisms, you can get blood clots, you can get all kinds of stuff, because it's just swinging your body like this. And so, but Felix, this guy that went up the Red Bull thing, he was falling at, well, obviously supersonic speed, and they didn't know exactly what would happen, but he came out of it, and he ended up, he didn't free fall as long by 16 seconds before he pulled it, but he, well, here.
Whoa, that's so high.
So you got 5 minutes to watch this. Keep watching this. This is the first time.
Air Force balloonist Captain Joseph Kittinger Jr. is laced into an elaborate pressure suit in preparation for a daring ascent into the stratosphere. Kittinger, who weighs 150 pounds, packs 155 pounds of suit and equipment. The scientific goals of Kittinger's ascent are to test a new 6-foot stabilizer parachute designed to keep an ultra-high altitude jumper from spinning and blacking out before he can open the main chute. The balloon reaches a height of 19.5 miles.
52 years later.
Sponsored by GoPro. That's great.
So I was 52. Oh, this 52 years later from 1960, that's right.
That would have been so scary. I wouldn't have wanted to jump that high in my life.
What was this? Curiosity.
Okay, do you read me, Felix? Activate suit and chest pack cameras.
I want to do it today. If I can get to do it. Brian's fancy.
So he had all these GoPro cameras on him.
That's why it's on, probably there.
The transmit cameras are on the configure red lights.
Felix, disconnect the oxygen hose.
Okay, he switched to oxygen in his suit. Use it without.
Okay, Joe, we're ready.
Right on the edge.
Yeah.
There it is, there's the world out there. seatbelt. All right, stand up on the exterior step, keep your head down, and our guardian angel will take care of you.
Get the hands out.
Release the helmet tie-down strap.
Why did they do that?
Release the tree. What I can see. Sometimes, yeah, if you're not really high. The smaller you are. I'm going home now.
And he just reached terminal velocity.
That would have been so.
It does lock.
When you see.
Wow, look at that.
The temperature of the earth, all the flat earthers are wrong.
Yeah, that's why we
You're right, it's the coin.
It just feels like it's so scary, but after you experience the first push, it's like, hey, I want to do it again.
I don't think anybody wants to do
Depends if you're in a rush to. After the rush, you get from this, you're gonna probably chase it.
it. It doesn't even look real. Oh, these guys.
Now, this is slow motion, but he's traveling at hundreds and hundreds of miles an hour.
So it's actually really fast.
Really fast. I mean, he gets up to 800 miles, over 800 miles an hour.
See if you can get a respiratory count.
So he is screaming.
Speed 546.
Speed
Wind forward 25 seconds.
Speed 600 miles per hour. 650 miles per hour.
I wish they were real. I wish they were real.
There's a miles per hour airspeed down there.
Heart rate's out of
Give it, you got it? Anybody to stand in? 1 minute free fall.
He is.
Good evening. I have been following speed for a long time. Sounds like I have a bad house.
It's increasing in speed.
I mean,
Where's he jumping over?
Stable as a rock.
Where's he jumping over?